All right, good day, everybody. Welcome back to another live stream at a different time today. It's at a different time today because I've got a crazy day today. And you also might be noticing actually that like the video might be a little bit scrunched, if you will. So the problem I'm having is that last week I decided to wipe my MacBook from just from the start, as if I just purchased a brand new MacBook, just to reset everything up and clean up my environments and whatnot. And I kind of forgot about about setting up my Streamlabs setup. So the Streamlabs is the product that I use to actually do these streams. And so yeah, actually, I should probably do a quick audio check just to make sure that even the audio is working, because I have done one of these streams before. Okay, the audio is working. I have done one of these streams before where I got 40 minutes in and realized the microphone was disabled, and yeah, not fun. All right, so let's jump into our topic today. So this is actually going to be a two-parter, and so part of the reason that I am doing this stream at a little bit of an earlier time is I do have to get back to my regular day job. I got some meetings this afternoon. So this will be a little bit of a shorter stream, and then I think that we'll talk about part two in a little bit, but I think it makes logical sense to parcel out what we're going to talk about today versus what we're going to talk about in the next stream. So let's talk about MLX. So what is MLX? So this is a new Python framework, machine learning framework that Apple, the same Apple that makes the iPhones and MacBooks and stuff, has recently put out. I believe they launched it out in December. It's still kind of in a little bit of a beta status, but it's fun to work with. And so what is the value of MLX? So you might be familiar with other frameworks such as PyTorch or TensorFlow. This transparently is another one of those frameworks that is very similar to that. And so you might be wondering, well, why do we need yet another framework for these sorts of things? So the real benefit of MLX in particular is that, so as you may or may not be aware, a couple years ago, Apple decided to get into the game of manufacturing their own silicon chips, known as the Apple silicon chips. You may know them as the M1 or M2 or M3 chips. So this was a departure from the past where they were using Intel as a supplier for that. And these chips are really great. I mean, they are blazing fast, not just for machine learning, but for video processing. Like video editors out there will tell you, like these machines are blazing fast. And so the idea here with MLX is, can we make use of this Apple silicon hardware that we have here to do some really cool things? And I guess that it's not really just limited to Apple silicon hardware. This will actually work on if you develop apps for iOS or iPad OS or Vision OS, it makes use of I'm drawing a blank here. It makes use of Swift, the programming language Swift, and so actually there is a flavoring of MLX that works with Swift. So the thing that's really cool, and I'm not actually going to officially recommend this app because I think it's more of a proof of concept than anything. But there actually are apps out on the App Store today. You can't really see this well, can you? But like this app here is where one person demonstrated how they could get a large language model running on this device. And so this is an iPhone 14 Pro Max. This is last year's model, or I guess 2 years ago, technically model. But it does a really good job. And so I think the promise here is that how can we start to make better use of the hardware that we have on hand? So I'll just say, I personally, this might surprise folks, I don't have a GPU. The only GPU that I have is just whatever's inside my devices. I actually don't have any GPU or any of the NVIDIA 3090s, whatever. I don't have any of that. And I personally don't see a need for myself to need one, because I can do the cloud-based stuff. So whether that be from the Lambda Labs or AWS, there's definitely options out there. And so I personally just don't see a need for it myself. Yeah, so the cool idea is, can we make use of the hardware on the Mac? So like I said, so you could use those other providers out there for GPU usage, but they come at a cost. And so for example, if you want to spin up a AWS SageMaker notebook with a GPU instance running behind it, I believe that's something like $2 to $3 an hour, which is not terrible, but it's still $2 to $3 an hour. And if you're not careful, if you don't shut down that notebook and you leave it running for 24 hours, well, now you got a nice little bill for you. So what the stream is here is going to be intended for today is largely how to make use of our own hardware to run large language models. But let's just jump into the screen here, and let's talk a little bit more about MLX holistically. So let me share my screen here. By the way, I am monitoring both LinkedIn and YouTube for questions, but not X. I still don't know how to do that. Yeah. So I see a comment in the chat there, a person saying, "I'm curious why Apple decided to go with Python instead of Swift first." Well, they went in tandem, so like Swift is actually out there. But if I don't know if like Python came just like a hair before that, but like if I had to guess, most of us folks who work in the space work in Python, so that kind of makes sense. But yeah, there already is a Swift element out there. Now, transparent. Like I would love to learn Swift. It's just I don't have the time yet. Like, all right, so let's look at the quick start guide here of how MLX kind of works. So for those of you who are familiar with PyTorch, or like the syntax is very similar. In fact, like when we actually get into some of these things, like you'll see like what MLX kind of looks like. Well, actually, not so much. I lied about that. You're not gonna get to see the super details about MLX. And part of the reason that we're not gonna really get into the weeds of like doing these sorts of syntactical things is that Apple has done a fantastic job at providing this GitHub repo over here that provides many different examples of how you can run different things. So each of these directories in here represents an example of a different type of generative AI model that you can run using your MacBook hardware. So like, for example, this lava here, this is actually, so you might be familiar with GPTV or GPT Vision. So that's where you can take a picture of something. So like if it took a picture of my office right now, it would give back a textual description saying, I see a microphone, I see a guy wearing glasses and a watch, and I see a bookshelf behind him, et cetera, et cetera. That's what this is. And I actually did get to run this on my Mac. So I do want to talk a little bit about hardware restrictions here. Even though MLX will run on any Apple Silicon Mac, now I want to be clear, it's Apple Silicon. So if you have an Intel-based Mac, this unfortunately won't work. But even if you have a MacBook Air or a Mac Mini, this would theoretically still work. But like this lava, for example, I did pass a single image through it to get just a little bit of text back. And it took a full, like, I don't remember exactly, somewhere between 5 and 10 minutes, like a total of 5 to 10 minutes just to get like a single sentence out of that. So, and that's one of the challenges that you'll have here. And I actually, so if you're unable to stick around for the full stream, I actually do have like I pushed this notebook out to GitHub explaining these things. So like, and I have this section here called YMMV, your mileage may vary. And the reason I bring that up is like, so even though MLX can technically run all these things, like, so like, let's say I downloaded the native version of Mistral 7B, which is actually the model we're going to be working with. So I am running a MacBook Pro. This is my personal MacBook, a MacBook Pro with an M1 Pro chip and 16 gigabytes of RAM. That is just not big enough to run Mistral 7B. And in fact, like, I don't know, I think maybe Phi 2, so, or Phi 2, I don't know how to pronounce that, but Phi 2, like the model that Microsoft recently put out, a very small model, I think I probably could run that one natively. But otherwise, like most of these other models are still too big for my Mac hardware. So that's why this MLX stream is entitled Quantization with MLX. So let's talk a little bit about what quantization is. Like quantization is this idea of, so like when we actually train a model, a predictive model, or a large language model in particular, we're saving those weights of the neural network as generally speaking, float 32 data types. That's not a hard and fast rule. It could be float 64 or some other data type. But the value of a float data type is that it can get very precise. Like it has this very, very, very wide range of values. But then that also comes with a little bit of a downside, at least in my case. So the downside here, there's actually two downsides. Number one downside is that, the precision of this model, like the float values are just so big that it increases the file size of what you can run, which is why I can't run Mistral 7B on my personal MacBook. And then I can't remember. I can't remember the other reason now. Let me jump over into this little image here. So like, I actually like this image over here. So what quantization does is it takes the float values, whether they be float 32 or float 16, and it compresses them down into something that is smaller. So you can see here, this is a nice little picture of that, where it takes these different values here. So you might have, somewhere between like, actually, this is not a good let me find if I can find a better representation of the wide range of float 32 values. But anyway, I guess the thing I want to highlight here is when you perform quantization, what you're actually doing is you're taking values like this 0.1357, and changing it into something that is more like this. So you will see that 0.1357 turns into 14, negative 0.98 turns into negative 99, and so on. Now, the one thing I do want to be clear about here is that we're losing information. We there's no two ways about it. Like the precision here is very valuable, and because we are losing information, this means that quantized models are not necessarily as performant as their primary counterparts. However, they still are considerably performant. And we'll actually demonstrate that here later on in the stream. So back to this image, or maybe is there another image in here that also kind of illustrates this? Maybe this one. No. Well, basically, like, as you can kind of understand, we're taking this whole range of values that are in float 32 and compressing them down into something like int8. So int8, if you're not familiar with that, that has a range of values that spans between negative 127 and 127, as you can see here in the picture. And part of the reason I don't like this picture here is because it actually does not represent the full span of the float 16 values here. Like, the full span of this is way larger than negative 4.35 and 4.35. It's magnitudes larger, which is why I'm a little bit hesitant to show this picture. So that it compresses it down, and then it allows us to run this on our local hardware. And so that's what we're going to do here today. So let's actually jump into some code here. And like I said, if you're not able to stick around, that's okay, because we got this whole big notebook. But let's just jump into our main notebook here. Now, actually, we are going to be making use of Hugging Face behind the scenes to actually download our model. So let's go ahead and give a very quick little tour of Hugging Face. So this is, I'm logged in here, authenticated as my own user. So if we wanted to go and look up, so like I said, we are going to be playing around with Mistral 7B. And Mistral 7B, if you're not familiar, is an open source model that the weights and stuff are stored out here on Hugging Face and then other sources, and it has very good performance. So we can just go into this search bar up here, and we can just search Mistral. Okay, so you can see here, we got a couple different Mistral models. So this is Mistral AI, all of the models that they've uploaded to Hugging Face here. And you can see that we've got the, we're actually going to be making use of the instruct model v0.2 here. So this is the one we're going to be making use of. But I do want to call it here. For example, we have Mixtral in here. And Mixtral, if you're not familiar, is a much larger version of Mistral. It's actually a mixture of experts models. So mixture of experts meaning you have 8 different models that are actually trained in a very specific domain. And then, like, at the time of inference, they kind of band together, if you will, and to produce the best result. And it's actually rumored that GPT-4 operates in a similar capacity, not necessarily 8 different models. But so the Mistral 7B model here is something like 28 gigabytes in size, whereas the Mixtral model here is like 100 gigabytes in size. And again, I have 16 gigabytes of RAM on my machine. So when I tried to, I can actually get the Mistral 7B to quantize and run on my machine, but when I tried to do Mixtral, it just failed out. So again, this is just going to be dependent on your hardware. Like if you have a Mac that's a lot beefier, and there are definitely people out there that have demonstrated that they, with their beefy Macs, that Mixtral will run, then that's great. I'm just going with what I have as my hardware, and mine is what I consider a base level Mac, meaning that when I purchased it, it is the 16-inch Mac, but it is the baseline 16-inch Mac. There is I added nothing to it. In fact, I think I bought it at Best Buy, actually. So if we want to make use of this model, what we can do here is, you could see here that we're actually going to be using the Hugging Face Transformers library. So we can actually, we're going to load it as this. From the transformers library, we can load the tokenizer and the model itself using this. All right, so let's go ahead and do this. And I actually, for a little bit of transparency, I actually did do this beforehand because, like I said, this is a 28 gigabyte download. And so depending on your internet speeds, that could take a while. So I went ahead and cooking showed this. When I mean cooking showed this, I mean I pre-prepared everything beforehand, just in so like on cooking shows, they prepare the meal like in like whatever, let's say a pie or whatever, and then like toward the end of the show, obviously it's got to be put in the oven for X amount of time, and they don't want to wait, and so they just pull out this other things and I already have this pre-made pie over here. And so that's what this whole idea is here. All right, so let's go ahead and just copy this string. And so if you have not installed the like the Hugging Face Transformers library, it's as simple as running this command here. So it's pip install transformers. Ignore my versioning there, and then you can see I've already downloaded it, so we're good to go. All right, so let's go ahead. I'm gonna set some. I want to save this model locally. Well, I already do have it saved locally, but I want to make sure that our MLX quantized version is also going to save locally as well. And I actually do want to touch on another form of quantization before that, so I'm getting a little bit ahead of myself though. So let's just focus for now on simply just downloading the model. So I'm gonna do a couple imports here. So I'm gonna import OS because we're gonna let me make this a little bit bigger for y'all. There you go. All right, so we're gonna import OS, and then from transformers, import auto model for causal LM, and then auto tokenizer. Now, if the word the prefix here auto, if that's throwing you off, just know that. So what's actually going on behind the scenes here is when like all these different models out there have different model architectures, and so what this auto model or this auto tokenizer here is actually doing is actually detecting the string that you put in there. So we're going to be putting in the Mistral string, for example, and then it's going to download it's going to automatically figure out that we want the architecture for Mistral. I actually believe it uses the LLM architecture. And yeah, so that's really all what auto means. So let's go ahead and do that. Now I'm going to set a couple other variables here that we're going to be making use of. So model name. So this is going to be Mistral 7B. The instruct version, the 0.2 version, and then I'm going to set my base directory. So I'm going to be saving these things into my models directory. And I intentionally do not having a push up to GitHub with my gitignore file. And then I want to set a couple more specific directories. So I'm going to set BNB directory. Don't worry about what BNB means right now. We'll talk about that here in a little bit. BNB directory is base directory / BNB, and then we're going to set our MLX directory. So this is where this MLX directory is eventually where our model is going to be saved. All right, so equals F base directory / MLX. Okay, so that is that. Now I do want to conjoin these to be a little bit more specific. So I'm going to call this model directory equals F base directory. You know what? I'm just going to copy and paste this. we don't need to belabor the point. Y'all know what F string formatting is. So we're just setting a couple directories that we're going to be saving things to. We actually won't be making use of the second one, but we'll talk about that here. What this here is in a little bit. Okay, so like I said, in order to actually make use of the or download the tokenizer, what you would actually want to do is if you want to make use of the transformers library to download these things, you go tokenizer equals auto tokenizer from pre-trained, and so we want to then pass in our model name here. So this model name is we're just going to pass in the model name as such. Okay, and then we are going to do the model equals auto model for causal LM, and then a dot from pre-trained, and then model name again here. Okay, so that will actually download our things. And then if we wanted to save these to our file, the way that we do that is go to tokenizer.save pre-trained, and then we save directory is going to equal our model directory, or our model.save pre-trained is going to be save directory equals model directory. And this is really it. This is all we need to do to actually run or load and save this. Now, I'm actually not going to run this because, like I said, I already did this. So let's go ahead and look at what this did. So, so CD models. All right. So CD Mistral. So you can see I've only got the Mistral AI, and then Mistral 7B instruct. Mistral 7B instruct. All right, so let's just do a list out on what we got here. So what we have here is we got a couple files. We have the couple configuration files, which are basically just letting us know some metadata and configuration attributes about the model. And then the actual model itself is represented by these safe tensor files. So you can see here that that Hugging Face has split these down into like 6 different files. Now, one thing I'm a little bit confused about is if you actually download the Mistral from like their direct website, the file pathing is a little bit different, and let me show what that means. So if this is the tar file, I guess this is v01, but the same idea. So we still have the tokenizer, we still have the parameters as one JSON file, but we have all, like, I believe what's going on here is that like all these safe tensor files are the equivalent of this PyTorch path here. That are just consolidated together, and I personally don't understand why this is the case. I imagine it's something to do like because when you upload these models to Hugging Face, I'm gonna imagine that they're intentionally doing the split out. I just don't understand that. But that doesn't matter for this stream, not necessarily. So I'm gonna comment that out. So again, that's doing that. So let's talk about our first kind of quantization here. So in the end, we're going to end up using MLX, but because this is a stream a little bit about quantization as well, I do want to talk about the more popular way to perform a quantization, and that is with the bits and bytes library. So bits and bytes is this Python module also maintained by Hugging Face that allows very simply for a user to quantize a model appropriately. And so the way that we do that is we actually cannot demonstrate this effectively because this actually does not run on Mac hardware. So that's but I assure you this all does work if you were to go out into a SageMaker notebook or whatnot. So the way that we do that is from transformers import bits and bytes config, right? Hold on, I gotta look at my notes. All right, from transformers import bits. Oh, that's why. I was wondering why it wasn't autofilling. And bytes config. Now, even though we are importing it here, you actually do have to do a pip install on your own of the bits and bytes configuration library, as well as the acceleration library, the accelerate library. And I talk about more about that in this notebook over here. But like, we're not really going to be making use of this because again, this actually does not run on Mac hardware. But I still wanted to show it anyway. All right, so we import that config, and so that's why we're labeling this up here as BNB, representing bits and bytes. So our bits and bytes config, let's go ahead and set that bits and bytes config equals, all right, let me scroll down, look at my notes. All right, bits and bytes config, and then we just need to pass in a couple values. So we're gonna do load in 4-bit equals true, and then we're going to do BNB 4-bit quant type is going to be NF4, and to be completely transparent, I don't know what that data type is. I needed to do a little bit more research on that still. And then we have 4-bit use double quant, that's going to be true. And then finally we have BNB 4-bit compute D type equals torch dot b float 16. So there is another dependency here on PyTorch in order to perform this particular quantization here. And then the way that we apply this is actually very, very, very similar to what we did up here with loading our model, and that is So the tokenizer is not going to get quantized because there's no sense in doing that. So we'll just bring that back on down and not make 0 alterations to it. And then in order to apply this quantization to the model, so what we would do is model equals auto model causal for LM from pre-trained, and then we want to pass in our model name, and then we want to pass in another parameter called quantization config. Oh my gosh, if I can type right, equals BNB config, and that's it. Like, this is really pretty simple. And then like, if you wanted to save it out to the file, you would just basically do the save pre-train thing. But that's really it. And like I said, we're not going to be able to run this just because like this bits and bytes configuration stuff actually does not run on the Apple Silicon hardware today. I imagine that'll probably be updated at some point, but this will not work for us right now. And it doesn't matter because we're focusing on MLX anyway. All right, so let's actually now move into MLX, and we're moving at a pretty steady clip, and we're actually on the home stretch already. So the way that we can do this in MLX is actually rather easy. So I talked about before in here about how they have about how Apple has all these different examples, and in addition to the examples that they've created, they actually have created a subsidiary library called MLX LM. And so so you can do a pip install here of MLX LM, and basically what this is this is a clean, easy way to get up and going to just load models on your MacBook and then do a very quick quantization. The way that we make use of this, so let me look at my notes again. I'm gonna scroll. All right, so we need to do a couple of imports. So I already did do my pip install appropriately. So from MLX LM, we're gonna import 3 different functions here. We're gonna import load, convert, or I'm sorry, not. Well, yeah, we do want to do convert, load, generate, and convert. So these 3 are pretty straightforward. So load is loading the model and the tokenizer. Generate is generating inferences, which we will demonstrate, and then convert is doing that quantization. All right. So technically speaking, if you just wanted to get up and going very quickly, you could just we could just go model or tokenizer, comma model equals load, and then we'd pass in that model name. So this would actually download it from the web, but it's kind of doing a download from the web in a unique way. So let me demonstrate what that's doing, because I had to look into this. All right, where is nope, I didn't want generate, I wanted load. Oh yeah, it's in the utils file. I forgot they stuck it in there. The utils file. I've spent way too much time in this repo the last couple days, so I know this particular MLX LM repo like the back of my hand. Okay. All right. Where is snapshot? Snapshot download. Okay, so the way that they're doing it is instead of doing like a download like we're doing, is they're doing this snapshot download thing here, and there's nothing wrong with this. It's just that if you may work at a company where like this might be blocked because this is doing more of a straight like clone, and so generally speaking, companies don't like that. So the reason I'm sharing this other path here is because we can still make things work if we just go through this other way, and then if you work at a company where one of these things is blocked, then you can still make use of this appropriately. Hint, hint, wink, wink. So that is like in. So we're not going to actually make use of that. So what we want to do here is, if we want to perform our quantization, is we just need to provide the file path to our already downloaded file, or our already, I can't speak, our already downloaded Mistral 7B, and we can go ahead and do the quantization appropriately. All right, so let's, so the tokenizer, all right, so tokenizer is not going to be changed. So what I'm going to do is I'm going to say tokenizer equals auto tokenizer from pre-train, and I'm going to pass in the model directory again, and then we're just going to save this back out to the new directory. So nothing here too fancy. Equals what is this dot save direct. All right, so tokenizer dot save pre-trained save directory is which recommend. Okay, I got a question here. Which configuration do you recommend to do fine-tuning and inference of this Mistral model? We'll get to that in a little bit. I actually don't have a strong recommendation. We're just going to do the default stuff that MLX provides. So, but good question. Actually, that's a great question, because like that's one of these challenges here with quantization or just running with these models is it's really, again, dependent on your hardware. So if you have like if I had a 32 gigabyte RAM in my computer, we wouldn't even need to do this quantization. Like, this is just because like I don't have the hardware to be able to do this. So you could technically quantize down to 3-bit. You could quantize down to 4-bit. So 4-bit is the default. And I'm just sticking with that just because it works. But that's a great question. Like, again, your mileage may vary. YMMV. So save directory here is going to be our MLX directory. So pass through there. Now, the one thing I am going to do here is just save on memory, and so things just don't blow up on me, is I'm going to delete the tokenizer as a variable here. So after this is saved and pre-trained, then this variable goes poof and goes away. All right, so let's now talk about the model. The model is going to be a little bit different because we are going to be doing our quantization here. Okay, so in order to do the quantization, we just need to, we're going to have this convert path here, and we just have a couple of parameters that we need to pass in. So HF path here, this can be a little bit confusing. So HF obviously stands for Hugging Face. So Hugging Face, we're actually going to be passing in the, like I said, we could be passing in something raw from Hugging Face, but we are actually going to be passing in what we downloaded already. So that is going to be our model directory. All right, and then we need to provide another path. So we're going to call this, so this next path here, MLX path here, this is basically where we're just going to output our quantized model. So we already set this above, so we're going to call this MLX model directory. And then simply, we just need to pass in this other parameter here called quantized. Now, you can see here that you can provide those additional parameters of how you want to quantize. But again, I'm sticking with the defaults. So quantized group size, we're going to stick with 64 qubits. We're going to stick with the 4-bit, et cetera, et cetera. So the only thing that we need to do here is true. Now, before I run this, I'm a little bit scared to run this, and I'll tell you why. So about a year ago, I did a stream sort of like this that was using some deep learning stuff that was very computationally expensive, and I did not consider the fact that it would bomb my stream. So I'm very scared. Like, we'll go ahead and run this, but I'm scared this might bomb out my stream. So fingers crossed. Fingers crossed. All right, let's go ahead and run it. All right, so you can see, all right, so far so good. Let me check. I don't see that we're bombing out the stream yet. It takes about 25 seconds to do this quantization on this, so it's not too bad. All right, so just waiting for a little bit. Are we dead yet? All right, we're not dead. So I'm also afraid to do inference because I'm afraid of that same thing. Okay, so the quantization's already done. So let's go ahead and go look at that now. All right, so open. All right, so CD MLX, CD Mistral. So this is the quantized version of Mistral now that we're gonna be showing here. All right, so no hub. Or no, I'm sorry, not do sh. All right, so do that just stands. This is a little shell thing that stands for, I think, disk utility or disk usage, and this sh basically just compiles it. So you can see that we've actually effectively quantized the model down into basically 1/4 of its size. Is my math right? No, my math is wrong. It's 1/7 of the size, because the original file size was around 28 gigabytes, and now we've quantized it down to 4 gigabytes. And so, yeah, and you could see that we've saved our safe tensors appropriately here, and then we have all of our configuration stuff. We just did a straight port over of the tokenizer. So now we're ready to go for inference. And so inference, again, is pretty straightforward. So let's go ahead and demonstrate how you do inference by making use of this generate function. So I guess we're actually, well, oh, no, we do need to use the load function. My apologies. All right, so let's go ahead and load the model and the tokenizer. So model tokenizer equals load MLX directory. All right, so this is going to take a couple seconds. Again, fingers crossed that this doesn't bomb my stream because I did not think about that. So, all right, so we got the tokenizer, we got the model. All right, so let's go ahead and just set a prompt. So, the prompt here does not matter. Let's just say, give me a recipe for delicious chocolate chip cookies. All right, And so then the way that we actually make use of this, so we're going to say response equals generate. So this is that function that we loaded in from MLX LM. So model equals model, tokenizer equals tokenizer, your prompt equals prompt. And you'll notice here by default, the max tokens is actually set to only 100, which is extremely low. Now, the one thing I have noticed is if you set this too high, that it kind of, again, this just might be a YMMV thing. Your mileage may vary. This just might be another one of those things where my hardware is just not good enough. But we do want to bump this up a little bit. So I'm going to bump up the max tokens just so we can actually get a sufficient result and not one that just cuts off mid-sentence. All right, so max tokens equals 1,000. I'm going to just call it 1,000. All right, and then we can print the response. So this should, now I don't know if it's possible to stream out results. So this is going to like it, and when I mean stream out results, I mean, you know, if you play with ChatGPT, it does that word by word kind of thing. That way you can kind of see the outputs as it goes. This is not going to do that. This is just going to give us the full thing at once. So let's go ahead and run this. And again, fingers crossed that this does not bomb out the stream. Okay. All right. And it's relatively quick. Like it looks like it's taking a while, but that's because you'll see here in a sec. Okay, there we go. So after 13 seconds, here's all the tokens that were produced. Actually, I believe if we set verbose equals to true, it'll actually tell us how many tokens were streamed out per minute or a second. Oops, forgot a comment there. Oh, wait. Oh, look at that. Look at that streaming. I did not know that it actually did that. Okay, so you could see, look at that go. And this is actually a pretty good result here, as you can see. So even though we have quantized this down and we have, technically speaking, lost information by performing the quantization, this is not a bad result. And you know, we picked out a relatively simple example, but we could even alter this to say respond in the tone of Jar Jar Binks. Y'all know I love this. Jar Jar Binks from Star Wars. If you've watched past streams of me doing Gen AI, I always have to include a Jar Jar Binks reference. That's just me being silly. And you can see that I'm not going to try to do the Jar Jar impression, but you know, read it out loud in your head. And here we go again. So let's even. All right, so you can see, you know, we're really chugging here. Like, and again, this is the idea where we can do this on a Mac, or as I was saying, with the Swift version of MLX, you can do the same thing on an iPhone, and I think that's extremely cool, or an iPad, or a Vision Pro. So let's do one more prompt here. What do I want to ask? What is the airspeed velocity of an unladen swallow? Now, for those of you who are familiar, you'll recognize that as a Monty Python reference, and there we go. So most LLMs do get this correct, where it actually does print out the Monty Python reference. So oh yeah, you can see here that you know, we're getting 9.25 tokens per second, and the whole generation took well, I don't really understand what the two numbers there are doing, but yeah, this is really all you need to know. All right, so that really covers today's stream, and we're gonna go ahead and call it here. Like I said, I got a busy afternoon, so I'm gonna go grab lunch and get going. So in the next stream, what I want to do here is, well, actually, let me go back and share my screen here for a second. Is, you know, we got this working in a Jupyter notebook, but this is not an ideal interface. So in previous streams, we've used like the OpenAI API to build our own Gradio UI, and so as a reminder, Gradio is another library supported directly by Hugging Face that allows you to build these UI applications in the form of Python to basically make like a little pretty UI. And so that's what we want. That's what I want to do the next stream. Is I want to demonstrate is how we can wrap this all in a nice pretty UI. That way you have a really nice clean interface to work with on your computer. So you can imagine, you know, you go on a plane or you go on a train or a car or a bus and you don't have Wi-Fi and you want an LLM to work with. Quantization and MLX has your back. All right, so that covers today. The next stream, so next week is spring break. So I'm not taking any time off work per se, but I will be out. I'll be taking my family to Chicago next weekend, so there will not be a stream next weekend. But maybe in 2 weeks we'll do that secondary stream on wrapping this whole thing in that Gradio UI. So Hope you all enjoyed this one. We will catch you in the next stream. Have a good weekend.